All right, welcome back, class. We are going to talk through the rest of 9b, so this will be part 2 of 9b. And we just left off before we were talking about equations of lines. So the general equation for a linear function is y equals mx plus b. And if you notice, I'm just going to show you this really quickly in the calculator. If I am going to give, figure out some kind of stat. Oh, I guess I can't show you this. Here, let me pull it up. So if I'm modeling, which we sometimes will do, and you can actually do it on the calculator, if you notice these models here, if we're making a model, you can have a regular line model, which is ax plus b, or you can have a quadratic, a cubic, a quartile, or another line or a model for a line is a plus bx. Now they're using a's and b's and whatnot, but you notice that in this form we have, I'm going to write it in what you would notice it, y equals, first one is mx, slope, a is the slope and b is the y-intercept. So y equals mx plus b, and then you have another one, another form is y equals b plus mx. So the b is in a different spot depending on what type of equation you're dealing with. These are both linear equations, but this one is more of a modeling unit. We like the modeling part that goes along with this type of the function or this form of the function. So what that means is you have your initial value, which in the calculator it had a different variable, but b is your initial value. That's where the line crosses the y-axis, so like right here. All right, that's your initial value, and then you add to it the change in x times the independent variable. And that's generally your equation of a line. And I wanted to point that out before we go any further. When you see that initial value plus the rate of change times the independent variable, that means b plus mx. M is the rate of change, x is your independent variable. And that's where we get it from, and that's where we use, or what we use a lot of times when we're modeling data in our real world, as long as it's linear, as long as it has a constant change. So the algebraic equation of a line. In algebra, x is commonly used for the independent variable, as we know, and y for the dependent variable. And for a straight line, the slope is usually denoted by m, so we're generally looking at m, and the initial value, or y-intercept, is denoted by b. All right, and so then we place those symbols into our equation for linear function, and it looks like y equals mx plus b, linear function. All right, let's move on. If you want to see it in the form of a line, and you have this picture in your notes, of course, the equation of a line is in the form y equals mx plus b, where m is the slope and b is the y-intercept, and the slope of this line is 4. And that's because you rise 1, 2, 3, 4 over your run 1 to come up with the next point at an intersection. And of course it's at an intersection because we moved by specific units. We moved up 4 and right 1. At this point, we've moved up a certain amount and right a certain amount, but it's not on an intersection, so it was partial units. We still move to that point and it will still create the same slope. It's just we don't use it as often this point because it's hard to tell exactly where it ends, these parts that are in between values that are actual values. So anyway, the y-intercept, you notice is here. It's usually b, -4. Slope is 4, as you moved up 4 and right 1. And this would represent the equation y equals 4x minus 4, and it represents the straight line. It's a linear line. It's just same thing said twice. The slope of 4 and a y-intercept of -4, as we see. All right, so that's just something that we can look at. Varying the slope. Now, the effects of varying the slope on a line looks something like this. All right, a positive slope, which is represented by this reddish line, means that the line, as we move from the left to right, it's going to rise. All right, a negative slope, which is represented by the black line, as we move left to right, is moving downward. All right, so it's going to be like -1/2 or -1/3, something like that. And that means that it would slope downward as you move from left to right. And then the blue line represents a zero slope, and it it's 0 because it doesn't change at all. There's no change in y. It stays constant. And that would be a slope of 0. All right, now this is just a figure that shows what happens when you have the same exact slope, but the thing that is changing is the y-intercept. So this is the effects of changing the y-intercept for a set of lines, and they have all the same slope. So they rise at the same rate, and they're all positive slopes, but they cross the y-axis at different points. All right, if the y-intercept is negative, then of course it's going to cross below. It's going to cross the y-axis below the origin. If b is equal to 0, then nothing is added after the mx. You have nothing added, so it would be like y equals 1/3 x, and nothing added. And that means your y-intercept is 0, and the line then will cross at the origin. And then this red line has a positive b, and in that case, then the line would cross the y-axis above the x-axis. All right. Okay, so you're going to get a few examples like this in your homework. So we're going to go back to our notes. Do that with you on the notes. Just what I meant to hit. All right. The price of a particular model is $25,000 today. So a model of car. And it rises with time at a constant rate of $750 per year. How much will a new car of this model cost in 4.1 years? So we're going to use that function that we talked about, the model. So it's your initial value plus your rate of change times your independent variable. And this will be your dependent variable. So this $25,000 is your initial value, right? That's what the car is worth today. So that's going to go in the spot for initial value, $25,000. And then we need to add to it the rate of change. And this just tells you a constant rate of $750 per year. So that's our M. And then we have our variable that's independent as our X. And that's going to be y equals 25,000 plus 750x. So if that's your model, you're going to use that first, and your homework will ask for that first. And you can then use your model that you came up with to predict what the new car of this model will cost in 4.1 years. And in 4.1 years, that's your time. It's your independent variable, so it goes in for x. So you would just do 25,000 plus 750 times 4.1, and that is 25,000. Oops. Now you know why I get in trouble all the time. Plus 750 times 4.1, and that's going to be $28,075. All right. So the new price of the car after 4.1 years have passed will be $28,075. All right, so you'll be doing that a little bit with the homework. And then the last thing you actually don't have to do any of these types of graphs. I'll just do it quickly just because, but it used to be that we had to do graphing on our homework, but they took those out, so it's not really necessary. But just good reminder. So we'll move up 1 because this is your y-intercept. That's your initial value. It crosses the y-axis at 1, your initial value. And then 4 is what we see as the slope, but we know that that's really over 1, and we have the rise over the run as our slope. So from our initial value, we're going to add to it the change of 4 over 1. 4 over 1. And we can go down 4 and left 1 to continue the line to the left. All right. And that will be a picture of the graph. Initial value, 1, because that's where it crosses the y-axis. And then slope, rate of change is 4 over 1. All right. Well, good luck with 9B homework. Let me know. Send me an email if you have any questions. Be happy to answer them. Have a great weekend.